All right, into the home stretch, last week of class. Today and tomorrow we're going to go over kind of a different way to do things. Everything we've done so far has dealt with forces. There's a second way to do any sort of mechanics problem, and that is using work or energy. So this actually comes in handy a lot more in dynamics class when things are actually moving around. For statics, you see it's relatively limited, but again, it's good to see this as another way to do it. So to introduce these concepts, work and energy, need the definitions of them. So if I have a force and it causes a displacement, so I'm pushing on a box, for example, and I make that box move, I've done work on that box, and the amount of work that I've done is equal to the force times the displacement. So work done, or change in work done, change in energy kind of thing, is the force times the distance that it moved. And it only matters which, the only direction that matters is the same way I'm pushing it. So if I push a box to the right, it's only that right displacement that matters. If I'm pushing it to the right and it moves upwards, I've done no work on it because it's the thing that made it move up and down that did work on it, not me pushing it to the right. So because of that, we have a dot product, and that takes care of that. So if I'm pushing to the right, it's only the portion of this that actually moves to the right that actually matters. Because of that dot product, another way to write this in terms of magnitude is F times the displacement times the cosine of the angle between them. And this is usually measured in joules, which is equivalent to Newton meters, or in SI units in pound feet, force times the distance. Notice that moments are also forces times distances, but I generally write those as foot-pounds as opposed to pounds feet, to kind of keep them separate so you know which one you're talking about, because they're not the same thing. So that is one way to do work. You can also do work by rotating things. So similarly, anytime you do something in a linear fashion, there's usually a rotational analog to it. So there's also a rotational version of work. So if I rotate something by applying a moment to it, previous definition was force times distance. Here we have the rotational version of those. Rotational version of force is a moment. Rotational version of displacement is angular displacement. So the moment times the angular distance that it goes through in radians gives me the work done. For the linear case, whether work was positive or negative had to do with the dot product. So again, a dot product of the two, force and displacement. That angle between them can be anywhere from 0 to 180 or even more, but that takes care of whether it's positive or negative. If it's between 0 and 90, it's going to be positive work. If it's between 90 and 180, the dot product will give you negative work. Basically, if you're pushing in the same direction that's moving, that's positive work. If you're pushing in the opposite direction, it's moving, that's negative work. Same deal for the moments and rotational work. If they're going in the same direction, if my moment is applied in the clockwise direction and the rotation is in the clockwise direction, if they're both in the same direction, then that's positive work. Similarly, if they're both counterclockwise, if one's clockwise, one's counterclockwise, then it's negative work. Now, the problem with work in terms of statics, as I said, is kind of limited, is the fact that to get work, we need to have some sort of displacement. We need something to move. Either it moves linearly or it rotates. In any event, it needs to actually move to have any work done. If nothing moves, there's no displacement, there is no work. So in terms of statics, that's not very useful. So what we do is we use something called virtual work, which is kind of like an imaginary displacement, because again, statics, point of it is nothing's moving. So virtual work, I give it an imaginary or virtual displacement given by delta r or delta theta, or dr and d theta are the actual displacements. So slightly different notation again to denote that this is not an actual displacement, it's just kind of an imaginary displacement. And then from that, virtual work is defined very similarly to what we had before. Delta U is my force times my imaginary displacement times, again, cosine the angle between them. So again, that's my dot product, same as before. Or rotationally, my work is the moment times the imaginary rotation, if that's what is what's happening. And so because statics, nothing's moving, The principle of virtual work basically says that because nothing's happening, things to be in equilibrium, I need nothing to happen essentially, so the total work has to be 0 to make that happen. So if a body's in equilibrium, the sum of all the virtual works being done on it will have to equal 0. So that's another condition for equilibrium. So before we always dealt with our 3 equations, force in the x direction, force in the y direction, and some of the moments. If those 3 things were all added up to 0, then we had equilibrium. Here we only need one thing, and that's this virtual work to equal 0 for the body to be in equilibrium. This comes in handy when you have a bunch of several connected rigid bodies. So what we did before is we kind of broke this up into different parts and looked at the forces in each individual member acting at the pins and found all sorts of reaction forces at the pins and ended up with 9 or 12 equations for a whole bunch of unknowns. Virtual work cuts that down a lot. In terms of virtual work, what I need to do is I need to know all the forces, I need to know all the moments, then I need to know all my virtual displacements. And if my virtual displacements can be governed by one particular variable, so in this case, I have my variable theta down here, and whatever this value of theta is, that's going to tell me exactly where every point is on here. So this is always kind of my origin. This point here is going to depend on what the value of theta is. This point up here is going to depend on what the value of theta is. This point where the force is acting is going to depend on what the value of theta is. So this thing is completely described by this one variable theta, and that's what makes my life really easy doing it this way. And so based on this one parameter theta, if I change theta, give it a virtual displacement, then that's going to change the locations of all these things. If I change theta, as I said, this thing's going to go up or down. If this thing moves up or down, that's a displacement from this force P. So that force times that displacement is some form of virtual work. And then I take that over all my forces, all my moments on my object, and add them all up, and it should equal 0 for equilibrium. A very basic example is just this one cantilever beam I have here. I have some force P pushing up on the right-hand side. And so I'm going to give this some virtual rotation. So I'm going to assume that it gets rotated by some amount delta theta. Of course, I have some reactions. We all know about those, AX, AY, and my moment MA. So I've assumed, again, this is not what's really happening. I'm imagining this is happening. This thing gets rotated around this point A. If this thing's getting rotated around point A, in terms of my virtual work, moment MA can be thought to be causing this rotation. So that's going to give me some work that's MA times delta theta. So MA is going counterclockwise. Delta theta went counterclockwise. So positive work being done there. AX and AY have 0 displacement. So this point didn't actually move. So because this point didn't actually move, AX and AY are not actually providing any work to this. What is providing work, though, is this force P way over here. So this force P, again, could be thought of as pushing this bar up. If I'm dealing with radians, which I usually do in virtual work, then this distance that it went by is just L times d theta. And so work out of this is P times L d theta. So that's another form of work that's being done on my bar. For these 4 forces, or 3 forces and a moment, those are the entirety of the work being done on my bar. So you see both of these depend on this virtual displacement, delta theta. So I can pull that out. I'm just left with MA plus PL times delta theta. And principal virtual work, for this thing to be in equilibrium, that has to equal 0. Now I know that delta theta doesn't equal 0 because, again, I've imagined that it did actually go somewhere. So I'm assuming it does actually go somewhere. So what has to be 0 is the stuff in the parentheses. For this stuff in the parentheses to be 0, I need MA to equal negative PL. And that's exactly the equation you would get if you went back to the original beam, took the moment around point A, and you'll find that MA has to be exactly negative PL. So again, another way to get the same answer, but using a different system, instead of forces, using work, For this system, obviously, it's slightly harder, you will see, but for other cases, it's going to be easier. So it's good to have this second way to do things. So that's basically the point of lecture later today. We'll see examples. I'll go over that one again and go over harder ones where you can see that this system is actually better than using forces. And then tomorrow will be very similar. Instead of just focusing on work, we'll focus on potential energy, and that makes it easier for even harder systems. So I will see you later today.